One of the greatest scientific missions of modern times has taken a giant leap forward today with the launch at lunchtime of the James Webb Space Telescope, a 10 billion project that has taken 30 years to reach this moment. Telescope was launched from Kourou in French Guiana. It's the most powerful ever built, and developers hope it will reveal stars and galaxies from the birth of the universe. The observable universe refers to the portion of the cosmos that we can study and examine using telescopes and scientific instruments. However, our capacity to observe is fundamentally constrained by the speed of light, the universe's ultimate speed limit. Since light takes time to travel across the vast expanses of space, we can only see celestial objects whose light has had enough time to reach Earth. This means that there are regions of the universe, possibly teeming with galaxies or other structures, that remain hidden from us simply because their light hasn't arrived yet. In this context, the observable universe is both a vast domain of exploration and a natural boundary of our current understanding. Its diameter is estimated to be around 93 billion light-years, far exceeding the 13.8 billion-year age of the universe. This apparent contradiction is explained by the constant expansion of space itself. As the universe expands, objects that were once relatively close are now farther apart, and the light emitted from them has taken much longer to arrive, allowing us to observe regions now far more distant than might seem intuitively possible. Despite these inherent limitations, the observable universe offers an extraordinarily rich area for scientific study. Our knowledge of it continues to expand thanks in large part to breakthroughs in technology and the deployment of space-based observatories like NASA's James Webb Space Telescope. These advanced instruments have significantly improved our ability to explore the structure, composition, and history of the universe. They have provided valuable data on phenomena that occurred billions of years ago, offering scientists unprecedented insights into how galaxies, stars, and other cosmic structures formed. Among the most groundbreaking capabilities of the James Webb Space Telescope is its ability to peer back into the earliest epochs of the universe by detecting faint infrared light from ancient galaxies. By analyzing this light, researchers have been able to observe celestial bodies as they existed just a few 100 million years after the Big Bang, effectively giving us a glimpse into the universe's formative years. This ability to observe the distant past is largely thanks to a phenomenon known as redshift. As galaxies move away from us due to cosmic expansion, the light they emit is stretched into longer, redder wavelengths. The James Webb Space Telescope is specially designed to detect these wavelengths, allowing astronomers to study galaxies that are not only incredibly far away, but also existed at a time when the universe was still in its infancy. These observations have yielded critical information about the rate of star formation in the early universe, helping scientists understand how the first stars ignited and how early galaxies evolved. Understanding the conditions under which stars formed and galaxies took shape during these early epochs is essential for constructing accurate models of cosmic evolution. One of the most captivating aspects of exploring the observable universe is the possibility of discovering extraterrestrial life. For centuries, humanity has pondered the question of whether life exists elsewhere in the cosmos. Recent advancements, particularly the discovery of exoplanets, planets that orbit stars beyond our own solar system, have made this possibility seem increasingly plausible. Scientists have employed methods like the transit technique and radial velocity measurements to identify thousands of these worlds, some of which bear striking similarities to Earth. These planets have become prime candidates in the search for life, especially those situated within the habitable zones of their stars, where conditions may permit the presence of liquid water. A particularly intriguing discovery came from the James Webb Space Telescope, which detected water molecules in the atmosphere of an exoplanet called WASP 96b. Though not considered Earth-like in its broader characteristics, the planet's atmospheric composition, suggesting water vapor, clouds, and haze, was unexpected and significant. These features challenge existing assumptions about which kinds of planets might be capable of supporting life, or at least the building blocks for it. The presence of water is one of the most crucial factors in assessing habitability, and this discovery adds another piece to the growing body of evidence that potentially life-supporting environments might be more common than once thought. As we continue to study the observable universe, profound questions remain about what lies beyond it. The observable universe is, by definition, constrained by the distance light has traveled since the Big Bang. However, it is widely believed that the total universe extends far beyond this limit. Some cosmologists estimate that the universe could be at least 10 to the power of 23 times larger than the observable portion. This staggering possibility emphasizes how much of the universe is still beyond our observational reach. Since we cannot directly observe these distant realms, we can only theorize about what might exist there. One of the most fascinating ideas to emerge from this speculation is the theory of the multiverse. The multiverse hypothesis proposes that our universe might be just one of many, perhaps even an infinite number of parallel universes that exist simultaneously. This idea finds some support in quantum physics, especially in interpretations that challenge the classical notion of a single deterministic reality. According to the many-worlds interpretation of quantum mechanics, every possible outcome of a quantum event actually occurs in its own separate universe. In this view, what we perceive as random outcomes are actually different branches of reality playing out in parallel. While still speculative and lacking direct empirical evidence, the multiverse theory has captivated the imaginations of both scientists and philosophers. Some proponents argue that it could help explain the finely tuned physical constants of our universe, which appear to be just right for the existence of life and matter. Others are more skeptical, viewing the multiverse as an elegant idea that remains untestable with current technology. In addition to the multiverse, another enigmatic phenomenon that has stirred scientific interest is known as dark flow. First proposed in 2008, dark flow describes the unexpected motion of galaxy clusters that seem to be moving faster than predicted by existing models of matter distribution in the universe. The hypothesis suggests that some clusters might be influenced by a gravitational pull from a massive, unseen structure beyond the observable universe. This would imply the presence of either unknown matter or a deeper cosmic structure that exerts an influence on the visible universe. Some researchers have linked dark flow to the effects of dark matter and dark energy, two of the most mysterious components of the cosmos. Dark matter and dark energy do not emit light or radiation, making them incredibly difficult to detect directly. Yet they are believed to comprise the vast majority of the universe's total mass and energy. While dark matter helps explain the gravitational behavior of galaxies and galaxy clusters, dark energy is thought to be responsible for the accelerated expansion of the universe. The study of dark flow aims to determine whether these invisible forces are responsible for the peculiar movement of cosmic structures. However, the scientific community remains divided on the issue. Some studies have supported the existence of dark flow and proposed explanations involving vast gravitationally significant structures beyond the observable horizon. Others have questioned these findings, suggesting that the apparent motion might be due to errors in data collection or interpretation. Regardless of the outcome, the investigation into dark flow continues, underscoring how much remains unknown about the forces shaping the universe. The pursuit of understanding the observable universe and what may lie beyond it continues to inspire profound questions and relentless inquiry. From mapping ancient galaxies to studying the atmospheres of exoplanets and contemplating the existence of parallel universes, the search to comprehend our place in the cosmos is far from over. Each discovery, whether it involves the distant past or speculative futures, adds to our growing understanding of a universe that is as mysterious as it is vast. The technologies and theories developed along the way have not only advanced science, but also broadened our philosophical horizons, prompting us to reconsider the nature of existence, the possibility of life beyond Earth, and the ultimate fate of everything we see. In the end, the observable universe represents more than just a field of study. It is a window into the unknown, a canvas of light and time that stretches the limits of human imagination and ingenuity. As we continue to develop new instruments, refine our theories, and push the boundaries of what we can observe, the universe keeps revealing itself layer by layer. Whether we eventually discover life on distant worlds, confirm the existence of other universes, or uncover new cosmic phenomena, The journey of exploration ensures that the mysteries of the universe will remain a source of wonder and discovery for generations to come. As we deepen our understanding of the observable universe, the questions that arise become increasingly complex and profound. The boundary between what we know and what remains unknown continues to shift, shaped by new discoveries and the ever-evolving capabilities of our instruments. The more we learn, the more we realize just how much remains hidden, from the intricate details of dark matter and dark energy to the very shape and destiny of the universe itself. Scientists are not merely cataloging celestial bodies or measuring distances. They are attempting to decipher a vast cosmic story, one that spans time and space, and one in which humanity occupies only a small but increasingly aware part. One area of ongoing interest in cosmology is the geometry of the universe. The observable universe appears to be flat, meaning that parallel lines never converge or diverge over cosmic distances. This observation has been supported by measurements of the cosmic microwave background radiation, particularly from missions such as WMAP and Planck. A flat universe implies that it will expand forever, but at a rate that could eventually slow down or accelerate, depending on the role of dark energy. Yet even this seemingly simple observation opens up vast avenues of inquiry. Is the universe truly flat on scales beyond the observable horizon, or does it curve in ways we cannot yet detect? And if so, what would that mean for the ultimate fate of the cosmos? The cosmic microwave background, CMB, is another critical tool in our exploration of the observable universe. This faint glow of radiation, left over from the Big Bang, permeates the entire universe and provides a snapshot of what the cosmos looked like when it was just 380,000 years old. By studying minute temperature fluctuations in the CMB, scientists can infer a wealth of information about the early universe, including the distribution of matter, the rate of expansion, and the initial seeds that led to galaxy formation. These insights help anchor our understanding of cosmic history, but they also raise questions about what came before the period known as cosmic inflation. A rapid expansion that occurred in the first fractions of a second after the Big Bang remains one of the most mysterious chapters in the universe's story. If we could observe gravitational waves or other relics from this period, we might unlock secrets that go beyond even the observable universe itself. The study of cosmic inflation leads to even more speculative but fascinating ideas. One is that inflation may not have been a one-time event. Some models propose a concept known as eternal inflation, where pockets of space continue to undergo inflationary expansion while others, like our observable universe, stop inflating and evolve into isolated regions with their own physical laws. This theory feeds directly into the multiverse hypothesis, suggesting not just multiple universes existing in parallel, but an infinite ensemble of universes, each with its own unique properties.